We're going to talk about combustion. And combustion is more commonly known as simply fire. And we know that if we have fire, we end up with heat, and gas heating is all about having heat. Well, the official scientific name for combustion or fire is rapid oxidation. And you may think that's completely irrelevant, but I like you thinking of rapid oxidation because it makes you think about the science behind it. So we're going to get into the science of combustion, the science of fire, and the science of rapid oxidation. So one of the things my students laugh about is, oh, my house is on fire, we better call the mobile rapid oxidation suppression unit. It's just one of those jokes. So this we call the combustion triangle. It takes three things to have combustion, three things to have fire, three things to have rapid oxidation. We must have a fuel, we must also have oxygen, and we must have heat. Now, it's also easy to think of heat as an ignition source, such as a strike, an ignition, hot surface igniter, an arc, a spark, or just simply heat in general. Now, once we have this chemical reaction or rapid oxidation taking place, we end up with a byproduct of heat that helps keep this going. But if we remove any one of these from our combustion triangle, we end up losing combustion or losing fire. Oxygen is a key point of that. If we take oxygen away from our fire, we end up with no fire. You may have seen this when you put a candle inside of a jar or on a jar. It burns up all the oxygen, we have nothing left. Also, if we burn up all of our fuel, we have nothing left. Or even if we take away our heat, we have nothing left. So if we take away our oxygen, our combustion triangle falls completely apart. We no longer have fire. So these are what we're going to be talking about today. We must have the fuel, something to burn, and this can be many different things. We're going to be talking primarily about natural gas and propane. We must also have oxygen. So this is important because some of the new refrigerants are flammable, and we're going to have heat in the refrigeration system, and we're going to have fuel such as propane, a flammable refrigerant, but without oxygen, we cannot have combustion. So that's one of the key components. We must have fuel, we must have heat, and we must have oxygen all together to have this beautiful thing we call combustion or fire or simply rapid oxidation. So you're all familiar with the lighter. We have oxygen around us. In here we have a fuel source, but nothing's happening because we don't have any heat. Now when I press this button, there's actually a little arc going on right there, a little spark. So when I ignite this flame, now we have rapid oxidation, we have combustion, we have fire. So this is what we need. If I release this lever, we lose the fuel, so we no longer have the fire going on. So that is rapid oxidation. So another thing I want you thinking about when you think about fire or rapid oxidation is something like this. This is simply a sealed chamber, and I have a little plunger right here. So right now inside of here is some oxygen, and what we're going to do is add a fuel source to this. And the fuel source I'm going to use is going to be a piece of cotton. So this is going to actually be our fuel. So I'm going to stick this down inside of our system here. We're just going to push it down in there. And then what I'm going to do is I'm going to stick our plunger inside of here. So if you remember back at the very first of class, we talk about temperature and pressure and the correlation between the two. And Boyle's law and Charles' law and the law of perfect gases and all those wonderfully beautiful things. So I have a sealed chamber. What I'm going to do is rapidly increase the pressure. When I increase the pressure, I'm going to rapidly increase the temperature. Pressure goes up, temperature goes up, my volume is decreasing. So I'm decreasing volume, increasing pressure, increasing temperature. So we have a fuel source, the cotton ball. There's oxygen trapped in here. Now we're going to add heat. What do you think is going to happen? Well, let's find out. So there we had a nice little spark at the bottom. That was combustion. Our fuel source mixed with our oxygen, mixed with heat. We had all three together. Boom, we immediately had combustion. This is also how a diesel engine works. We use simply compression, which creates our heat. We have the diesel fuel and the oxygen from the atmosphere, and that's how a diesel engine is also happening with that combustion. So let's continue on with this study of combustion, and let's look at one of our most common fuels we're going to be using. We're going to be using natural gas, which is primarily going to be methane. So methane is quite interesting because it has one carbon molecule, and that's represented by the black, and it has 4 hydrogen molecules. So we also call this CH4. There's one C, and then H, there's 4 of the H's, so there's 4 hydrogen, so it's CH4. It's natural gas is primarily made up of methane. There's a few other things involved, but it's typically about 1,000 BTUs per cubic foot, but this varies dramatically by location and whoever's providing the gas. You can actually call your local gas company and find out how many BTUs per cubic foot that they are providing. And that's going to be important to know when you're clocking a gas meter or doing combustion analysis. So that does vary. So here is our nice, beautiful natural gas. Now we have the fuel, we also need to have our heat and our oxygen. So what we're going to do is add that to our combustion side. I'm going to have my oxygen molecule, and oxygen is O2. So there's 2 oxygen molecules together, and we're going to put in here 3. Now I only need 2 to have combustion, but that's scientific in a laboratory combustion. We always need to have excess oxygen. So we're going to have 3 atoms here of oxygen compared to our 1 atom of methane. So we're going to have a chemical reaction right here. We have the oxygen, we have the fuel, we add it to a heat source. It's going to be the combustion, the rapid oxidation, and we're going to separate these molecules and then reconnect them. So we're going to explore this right now. We have our fuel, and this is our methane. It's going to be our fuel. We have oxygen molecules, O2, 2 oxygen molecules together. So this is going to be my oxygen, and we need heat. This is going to be some kind of an ignition source. So we can use straight up heat. We can use a hot surface igniter. We can use a spark igniter. We're going to, boom, have a chemical reaction, rapid oxidation. It's happening very fast. So we're going to have that chemical reaction. Now, only really need 2 oxygens, but we always want to have excess. We only need 2 oxygens if we had perfect combustion, which is only available in a precise laboratory. We're going to be outside of that, so we're always going to have extra or excess oxygen to make sure we're good. So we're going to have this chemical reaction, and energy cannot be created nor destroyed, and also matter cannot be created nor destroyed. So all of these molecules that I have going into the fire are also going to be coming out. So we have our methane, we have our oxygen, boom, let's have our chemical reaction. We're going to end up splitting all of these molecules. And one of the things we have is CO2, and we're also going to end up with H2O, and we're also going to end up with H2O. So we have our extra oxygen left over, so we have CO2 as the byproduct, we have H2, there's 2 H's and an oxygen left over, and we have H2O, so water vapor is actually a byproduct of combustion. CO2 is a byproduct of combustion, and we have this little excess oxygen left over. This is our science behind combustion, behind rapid oxidation, behind fire. Everything that we put into fire, we end up coming out of it. So I end up with all those molecules burning. Anything you burn, you end up with CO2. We still have the same molecules. We also end up with water vapor. This is very important for a few reasons. When we have an 80% gas furnace, we have to keep the temperature of the exhaust high enough so that we keep the water vapor in vapor form, so it's drafting out. When we have a 90+ furnace, we take these molecules, we take heat away from them, and they condense into a liquid form. That's what's draining out of that secondary heat exchanger and the flue pipe. That's giving us an extra 970 BTUs of heat. But notice everything that went into the heat came back out of it. So we have our full combustion triangle: fuel, heat, and oxygen. Now, let's go into this a little bit deeper. And what we have going into our system is not just simply our molecule for methane, but we also end up with our byproducts of air. We have nitrogen. So this is going to represent N2 for nitrogen. So we're going to have all these little excess nitrogen that's not part of our combustion, but we need it as part of our air. So we're going to put our system back together. So let's take a look at this again. When we have oxygen in the air, it's not just oxygen. We also end up with nitrogen in the air as well. This nitrogen is not going to be a part of our chemical reaction. However, it is going to be in there in the midst of it. So we have our chemical reaction. We're mainly going to need these two oxygen molecules and also our methane. All of the other is going to come with it. So we're going to have our chemical reaction. Boom, we end up with H2O. Hydrogen 2, boom. Hydrogen, 2 hydrogen to 1 oxygen, H2O, water vapor. We're also going to end up with C, 1 carbon and 2 oxygens. Here's our CO2. We have these left right here, so we're going to end up with another H2O. Boom. We have complete combustion. We have some excess oxygen left over, and all this nitrogen that was in with it, the nitrogen also ends up coming out of it. Now, the reason the nitrogen is important is because it's not helping our efficiency, but it's extra molecules, extra energy going in here, and it takes away some of the heat to heat up this nitrogen, so it makes it less efficient. We're losing some of our heat from combustion just to heat up this nitrogen. Also, in some areas, they're very concerned with nitrous oxide. So that excess oxygen molecule that we talked about can actually break up for nitrous oxide. So we end up breaking this nitrogen molecule and putting it with this oxygen, nitrous oxide, nitrogen oxide, and we have the other one here, boom. This is something we really look to avoid. This is going to be a byproduct, and this is also causes air quality issues. So California is very upset about nitrous oxide and has a lot of regulations for that. But all the nitrogen just comes in and also comes back out like it's not even there. But it does take away some of our energy because we're using that heat to heat up those molecules. So let's go back to where we were and let's look at another scenario. We're going to have our molecule of methane. So we're going to look at this again. We're going to use 2 molecules of methane. I'm going to take the nitrogen out of the way just so we can see a little bit better, because we know the nitrogen that goes in is also the same nitrogen going back out. So we're going to take those out of the way. Now I'm going to have the same amount of oxygen. I'm going to have twice as much nitrogen and see what exactly happens. So we're going to, boom, we have our fuel, we have our oxygen, we're going to have a chemical reaction. So if we look at what happens with this, we're still going to end up with our H2O. H2O, H2O, but here, this is a carbon and an oxygen, so it's going to be a carbon monoxide. We got this other one, we're going to break it up. So now let's look at what we have. We end up with H2O. 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 But here is a piece of information that's very important. We have 1 carbon and 1 oxygen. This is carbon monoxide, 1 oxygen, carbon monoxide, CO. Here's another molecule of CO. So when we end up with incomplete combustion, improper combustion, we didn't have enough oxygen. Now we end up with carbon monoxide. This is an issue. This is going to be coming out that flue pipe. This is also what we worry about getting into the customer's house. This is a silent killer. There's a video just on low-level CO monitors and carbon monoxide alarms, and it talks about the issues with this carbon monoxide, but this is a dangerous one. We didn't have enough oxygen molecules. We need more oxygen molecules to make this into CO2. CO2 is the same thing we breathe out. CO2 is what the plants need to grow. CO2 has the political issue of the climate change. But CO, carbon monoxide, this is the killer. So we still end up with our water vapor, but we don't have enough oxygen molecules. We have carbon monoxide. That's bad. We want to avoid that altogether. So that's what we need to take into account to make sure we have enough oxygen. We want to make sure we have extra oxygen in here so that we don't end up with carbon monoxide, or at least the least amount possible of that carbon monoxide. Now, that is propane. Propane's approximately 1,000 BTUs per 1 cubic foot. So what is a cubic foot? Well, let's talk about that next. So here we have our natural gas, which is mainly methane. It's CH4, 1C, 4 H's. So just like our picture we have here, this is natural gas. And it has a specific gravity of 0.6. Air has a specific gravity of 1. So natural gas is going to be lighter. It's going to float up. But this is 1 foot by 1 foot by 1 foot by 1 foot by 1 foot, 1 foot, all the way around. This is a cubic foot, 1 cubic foot of natural gas. So that represents a whole cubic foot of these molecules right here. And if we saw earlier, we needed 3 times as much oxygen to burn this 1 amount of natural gas. So to make this 1 cubic foot of natural gas burn, we need what else? And if you said O2, then you are correct. So here I need 3 cubic feet of oxygen to burn 1 cubic foot of natural gas. This represents my oxygen, O2, oxygen, O2, oxygen, O2, and my natural gas, or my methane, which is CH4. So now I have everything I need to have proper combustion. So 1 molecule, or 1 cubic foot of natural gas, I need 3 cubic feet of oxygen. So it takes 3 times as more oxygen to burn 1 cubic foot of propane, or natural gas. This is important. Now let's stop and think. The air that we're burning is not pure oxygen. Nope, it is not. So to get enough oxygen to have 3 cubic foot of oxygen for this 1 cubic foot of natural gas, it takes a significant more air, and this is what we're going to talk about next. So our air that we breathe is 78% nitrogen. This is that N2. It's mainly N2. It's 21% oxygen, 21% of the air is O2, and 1% is other. So we're going to need a significant amount of this air to make sure we have enough for this to burn. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It takes 15 cubic feet of air to burn 1 cubic foot of nitrogen or methane. That's a significant amount of oxygen. It's a significant amount of air. Because air is only 21% oxygen, we're going to have 15 cubic feet of air to burn 1 cubic foot of natural gas. Here's what else is interesting. Think about how much is going out the flue pipe. So all 15 molecules of air, or cubic feet of air, plus the cubic foot of natural gas is all going out the flue pipe. That's only for 1,000 BTUs. So think about a 100,000 BTUs furnace. We'd have to times this by 100. That's a whole lot of air. So we need to make sure that we're not just thinking about burning our gas. We need to think about the whole combustion process. We need to make sure that we have enough air. And combustion air is one of the most overlooked things of gas furnaces. You must have enough combustion air. Now this is for natural gas. Natural gas is lighter than air, 1,000 BTUs per cubic foot. But there's another gas that we talk about. What if we were using propane? Propane has 3 different molecules of carbon. So propane has a significant more energy, and it has a whole lot more atoms of hydrogen. So if we were looking at a propane molecule, propane is going to take a significant more amount of air because we have even more molecules of carbon. So 1 cubic foot of propane, because it has more carbon, has a higher BTU content. We're looking at 2,500 BTUs per 1 cubic foot. Natural gas is 1,000 BTUs. Propane is heavier than air. It's 1.5, so it's going to be falling down to the floor. This is going to be an issue if we have a propane leak. It's going to drop to the floor, it's going to spool around, it's going to wait for an ignition source, and when it does blow up, it has a significant more amount of BTUs. Natural gas is lighter than air. I have to hold this box down because it keeps wanting to float up because it's lighter than all of this air. So it dissipates better. It also has less BTU content. So gas furnaces are designed for natural gas. We have to convert them over to propane. One of the things we do is we use smaller spuds and smaller orifices. This allows less of the propane to come through. Because it's heavier, we have more pressure. So we're having to push it, throw that extra propane in there with the higher pressure, but the smaller holes allow us to keep the air-fuel mixture the same. That's why it's very important that we use the proper steps when we're converting it from natural gas to propane. It's very, very important. So, natural gas leak, drafts up and out. Propane's heavier than air because it has a higher specific heat content, so it's going to be dropping down to the floor. So these are things we want to keep into account. So let's talk about this combustion air, the air that we need to have that fire. If we had a 90+ furnace, we're bringing this straight from outside, we're burning it, and all of this goes straight back outside. It's very simple. But if we're talking about a 80% furnace, we're having to get that combustion air into the closet. So it's very important that we get it enough into the closet and we get it in the proper space. So let's look at a few little codes so we can see about how to do that. So we're going to talk about the International Fuel Gas Code. It's been adopted by 42 states, the District of Columbia, New York City, Guam, and Puerto Rico. This is the go-to code book, although not everybody has adopted it. So there's going to be different codes for your local area. But this is typical through across the country. So first we're going to talk about an unconfined space. Think about a gas furnace that's going to be installed in a basement or in some kind of large room. We need to make sure that we have 50 cubic foot of air for every 1,000 BTUs total. So if this is in a room, we have to take into account the gas furnace and the water heater and anything else that's going to be burning and using oxygen. We need 50 cubic foot per every 1,000 BTUs. So that is allowed, but you got to be thinking as we seal houses up more and more and more, where are you getting this oxygen coming back in the house from? In the old days, it would come through the floors and the ceilings, the cracks in the walls, but now we want to seal our houses better. So as we seal the house better, we're not getting this oxygen coming back in like we need to. We can actually burn up the oxygen in the house and cause a negative pressure system. So even though it is allowed by code, I never like that. I think that will be changing eventually. So let's talk about another code, 304.6. Outdoor combustion air shall be provided through openings to the outdoors in accordance with section 304.6.1 or 304.6.2. So what we're talking about here is combustion coming from outside. If we're having a gas furnace in a closet, small basements, anything else, even in the attic, we need to make sure we have enough combustion air coming in. So this says shall be provided through openings to the outdoors. So we're going to have direct air come from outside. In an attic, we have gable vents and we also have soffit vents. It's allowing this air to come in to burn. If it's in the closet, there's usually tubes connected to the attic, allowing this combustion air to come from outside to the attic, from the attic into that closet space. So let's continue on with 304.6.1. it says 12 inches from the top and 12 inches from the bottom are required. So this is what we call upper and lower combustion air. From the very top of the closet, there must be an opening within 12 inches of the top and another opening within 12 inches of the bottom of that closet. And it's required to have 1 square inch per every 4,000 BTUs per hour. So in your furnace, they're rated by input BTUs. You're going to look at that number, and according to this code 304.6.1, we need 1 square inch per every 4,000 BTUs per hour. Now, this is very important. It also says if you have horizontal ducts, so they're going sideways, maybe straight through a wall, straight outside. Horizontal ducts require 1 square inch per every 2,000 BTU minimum free air. So if we have a 2,000 BTU furnace, we could have 1 square inch, except it has a little caveat there. It says it must be a minimum no smaller than 3 inches. So the smallest hole we could ever have is 3 inches. But I've never in my life seen a 2,000 BTU furnace. They're always significantly higher than that. I think the lowest one I see is 30,000 BTUs. So you'd use that to think about the size of the hole you need. On top of that though, let's talk about free air. Just because you have a vent that's the big enough square footage, length times width, doesn't mean you're having enough. You got to think about these vents having louvers, having metal blocking the hole. So if we had a wooden louver, we had the hole the proper size was a wooden louver, that wooden louver only has 25% of free air. So the majority of that louver is covered with wood. That means 75% of that's wood, only 25% is the size we need. So luckily, in my area, we don't have a whole lot of wooden louvers, but in your area you might. So you need to be thinking that wooden louver restricts a ton of airflow. If we have metal grills, the metal grill has approximately 75% free air. So if we had a metal grill, we would know 75% of that, we take our length times our width, times 75%, and that would tell us the size of the free air opening. If we had metal screens, now metal screens vary dramatically, but if we had metal screens, we're looking at approximately 97% free air. So metal screens have the least restriction. I want to make another note though. Some local codes and building codes do not allow any kind of a metal screen. So you want to check your local code to where you're working, your municipality, because those can change. And motorized dampers. Motorized dampers are interesting because they open and close. So in the summertime, they close off, so we're not bringing that less heated air into the house. But those motorized dampers are about 95% free air. So there's a whole lot of codes, a whole lot of numbers. This is just an introductory to it. Once you start reading codes, it's great fun just reading numbers, but it's one of those things we have to do. We have to learn how to read those codes and interpret the codes and never argue with an inspector. I've heard of people that argued and won, but that inspector then made their life and their job very, very difficult. So these are things we want to take into account. Let's learn from the inspector. Let's work with the inspector. Ask the inspector why, and could he explain it to you and show you where that's at, and use it as a learning experience, but don't argue with them in most cases. So combustion is extremely important. Let's continue on with our thought process for combustion. When we're dealing with gas furnaces, one of the big things I like to do is a combustion analysis. It's important to know how to clock the gas meter. It's important to know the input BTUs, making sure we're not overfiring the furnace. But another important step is combustion analysis. Now, if a lot of people say, well, that new combustion analysis stuff, it's not a new thing. Let me show you my first combustion analyzer. This was the Firite. It was a Backrack brand, and this one's pretty well worn out. I keep it for nostalgia, but this is my first combustion analyzer. We actually have this chemical that we had to put inside of here. We had our little filter and pump, and you can see it's just rotted completely up. But, oh no, my hose broke. It's been a rough ride, buddy. So we'd actually take a flue gas sample, pump it up into here, and this would chemically react and tell us our CO2, how much CO2 we had in there. We also used our thermometer, a high temperature thermometer, in that flue to determine our temperature, and we could use that to find our first combustion analysis. We have our kit that we had to go through, a little guide that we used through this to find out if our system was burning correctly. It was so important to make sure that we had proper combustion. We want to make sure that furnace is burning as best as possible. Then, as we went on through our technology, we ended up with these really cool plastic cases. But the plastic cases, we still had the same thing. We had the tubes, we had the combustion analyzer, the fluid, we had to keep up with when we changed it, and we still, oh, my fluid's been leaking. That was another problem we had. This stuff would leak and it would corrode up. Sorry, fella, it's been a long time since I opened you. And as we go through again, technology kept getting newer, and we got these nice smoother cases that we had, our combustion test kits. And this one right here, we had a cool little calculator that came with it. So we could actually move this up and down and our stack temperature. And this was our calculators before we had phones that did all these calculators for us. This was combustion analysis. It's not a new thing. Then we came out with these really, really cool ones like this. And this one we could actually plug in, and it had motors in it, and we'd drill a hole, we'd get our flue gas sample, we could set it all up, and we could calculate how efficiently our furnace was running. I remember having this and being so excited I didn't have to wear those chemicals or have those chemicals anymore. This I thought was absolutely awesome. But then technology got even better. Instead of having to carry this big giant case around and send this off to be calibrated, we end up with some of the newer stuff. Some of the newer stuff being my back rack kit here. We got our Combustion Analyzer fully digital system, and what's cool about this, digital readout, had a magnet on it. We have our temperature probes with it. It records not only CO2, but also recorded carbon monoxide, how much oxygen, excess oxygen was in there, and it calculated everything and told us how well we were running. Even better, we could then send this to a printer through infrared, and it would print out a report, and we could leave that report with the customer proving that this system was working like it was supposed to. Nowadays, we even go a step further, and we have a system called Measure Quick with Jim Bergman, and you can take all this information, put it into a phone, and it will record it and give you a constant report. And you can update that report every time you go do service work, and you can send a copy of that report directly to the customer. I'm going to send you a link for Jim Bergman's system and how he works with his combustion. So I'm not going to go into detail about how to do a combustion analysis. And the reason I'm not going to do that is because I want you to take a course to fully understand everything about combustion. I'll send you a link to Jim Bergman's YouTube page, and I'll also do a quick combustion analysis on a furnace, but this is not going to be a how-to for combustion analysis. If you want to learn combustion analysis, and I recommend you do if you're doing anything with gas furnaces, this combustion analyzer and fuel efficiency, there's a course that goes with this, and it's a massive amount of information, good quality information, so you understand combustion. You're not going to understand everything about combustion in this short little course, but right here, this course goes through all those details. You take a test on it. Also, they have a course that combines carbon monoxide at cleared and present danger with combustion analysis. You're not just looking at how the furnace burns, you're also looking at the whole house as a system. What's happening is we're exhausting gases out of the house. We're putting the house in negative pressure, leeward sides of the house, where that extra air is coming in from, and also how we can pull carbon monoxide back down the flue pipe and out of fireplaces. So many technicians go into a house and they say, oh my gosh, we have carbon monoxide, let's replace the furnace. And it's not always the furnace. There's a lot of times many other things causing this. Attached garages, fireplaces, negative pressure, the vent pipe, having the bathroom fans running, pulling air back in. All of these things can cause that. I want you to take this full combustion analysis course and fully understand combustion. And if you're doing anything with gas furnaces, I strongly recommend that. Now, not every company promotes combustion analysis yet. I'm hoping that one day they for sure will. And if you work for a company that does not support combustion analysis, I hope that you will spend the extra money to get one so you can do it yourself and know that your customers are safe. But let's say you're not ready for that step, that's fine. There are two books here I recommend. One is Refrigeration Air Conditioning Technology, and the other is the AHRI Fundamentals. Both of these books have a heating course and a heating section set up in them. I love both of these books. One book has some basic information, some great diagrams. It's easy to quick and understand. The other book I love because it goes into even more detail and it has even more facts in it. It goes into all the detail about different types of gases, the combustion process, and these books are fantastic to understand combustion and gas furnaces and how these systems work. It's a ton of valuable information. I reference these books all the time, and the more that you learn, the more that you go through, and the more that you work with, and the more that you see this information, the better you're going to be. So both of these books, and some of the information is covered twice, but it's okay when you read it one way and then read it again a different way, somebody else's words, somebody else's viewpoint. It just helps reinforce that. If you're an instructor and you don't want to carry these big books around with you all the time, Jason has put together this really nice gas heating course, quick, easy to see. It's from ESCO Institute, easy, quick reference guides when I'm teaching the gas furnace and I don't remember all those different little names. This is a quick, easy to carry with me course. So my students prefer to also buy this book, and it's easy for them to carry around in the study. So sometimes carrying the big books around is challenging. Hey, if you can, get all of them. I'm not the guy that likes to sit down and read, especially code books. Oh my gosh, I hate those code books, but they're required. It's part of what we do. The more that I reference and read this information, the easier it comes to me. I wasn't the guy that sat down like, you know what, let's just get a bunch of books and start reading. But gas furnaces, it's so dangerous. It has the potential for killing people. You want to make sure you understand everything about it. Don't just make it make noise and make it make heat. We want to make sure we understand it to make sure it's working safely, correctly. It's going to work for a long time. That comes from reading this information. Also reading the installation manuals of these systems. So important now. This new technology is changing constantly. The only way you're going to know and be prepared is if you get in to do the reading. And the more that you read, the easier it comes. The more you read these books, the more understanding you have. And then when you read the installation manual, the more sense that it makes. So I recommend learning, getting as much education as possible, and definitely take any class you can. The more certification classes you can, the better. Every supply house has some kind of a training in it. Some of them are just about selling products, but still take those courses because there's so much you can learn. Any chance you get for a certification, take it. A certification doesn't mean you know more than somebody else. The certification means you went that formal route and you put effort in and you have something else, whether it's for your own benefit of, hey, I accomplished this, or for an employer who may or may not give you a raise for it, or that new job that's looking for these things. Get that education. It's mainly for you up here. It's going to make you a better person, also help protect your customers, and nothing better than the customer saying, hey, I want you to come back to my house. I don't just want your company, I want you, and they're calling you by name. Makes you feel really good. And when you go out there, you're not guessing anymore. You're knowing, hey, I did a combustion analysis. I know the system's working good. I put in for my customer a low-level CO monitor, not an alarm, because I know the difference in that. You have your personal CO monitor with you because you know that you're protected anywhere you go. So this is the things you want to do. Grow, grow, grow. This is a quick crash course in combustion and how gas furnaces work, but there's so much more to learn. Never stop learning.